Hi, my name is Clifton. I'm an undergraduate in physics, and I am very excited to talk to you today about the experiments we've been conducting at the Picosecond test facility at UTA. Let's just start with what we do and why. Conducting modern physics requires that we observe things that are happening very fast, so we need to use photodetectors. Here's how that works. When an event happens, light from the event comes and interacts with this top layer here, the photocathode. During the process, energy from the light is absorbed, and every once in a while, an electron gains enough energy to break free. When the photoelectron comes in, it's going to interact with a microchannel plate. That's what this is. And so the electron is going to bump off more electrons, which in turn bump off more electrons. Whereas we had one electron coming in, we have a million coming out. And while we can't detect a single photoelectron, we can detect a million. The issue is that every once in a while, the electron we talked about gains enough energy to break an ion free. That ion's going to come back and hit the photocathode. This will cause a secondary afterpulse when electrons from this area are released. By analyzing the afterpulses under different conditions, we might be able to figure out a way to increase the lifetime of the tubes. These graphs are from the Layman experiment, the industry standard in phototube testing. One of his main findings is the ineffectiveness of tubes without an ALD coating. The Layman experiment is a wonderful one, but it is not without issue. In particular, all the tubes we see represented here were destroyed in the process of the experiment. There is also the issue of time. This tube has been active for 11 years and is showing no signs of degradation. The graphs here compare integrated anode charge with quantum efficiency. Now, quantum efficiency is just the likelihood that we'll get a photoelectron. We want a high quantum efficiency. When it goes down, the tube no longer generates photoelectrons, so it is useless. So the question becomes, how can we maximize the usefulness of these tubes? Well, we can hope to increase the lifetime by doing more testing. The issue is that testing is destructive. It destroys the whole tube and you can't use it again. But it doesn't have to. This is a scan of a small photodetector before and after testing at UTA. The most important thing to note here is that we were able to perform testing without destroying the whole tube. The damaged area is extremely small. Each square here represents a 16th of a square inch, which is about 2/5 of a square centimeter. Through research, we have developed a way to perform a lifetime test on a tube without destroying the tube. These tubes are ludicrously expensive, tens of thousands of dollars for this 2x2 inch one. So we'd obviously prefer that they not be destroyed during the testing process. The method works like this. We send LED light through fiber optic cables. Light will go towards the phototube we're testing, and it will interact with a very small bit of the tube. We will also be monitoring the LED light through this photodiode, so that we'll know if there are any problems with the LED. Now the scan you see here is of a 2x2 inch phototube. It's very small. So the obvious thing is to make a big one. This is the large area Picosecond photodetector, or LAPPD. This phototube is 20 centimeters by 20 centimeters, and the cost per square centimeter is lower than smaller tubes. Here on the left we have a scan of the LAPPD before it was shipped to us. The square here represents the area that was irradiated. It's very small. During testing, this area received 5.6 coulombs per square centimeter of integrated anode charge. 5.6 is right here. The crucial thing here is that while this tube took 11 years to test, this tube took 30 days. And as you can see, there is no perceptible change. This is huge for a number of reasons. We were able to perform testing on this tube without destroying the entire thing, and it only took 30 days. While the tubes from the Layman experiment were unusable afterwards, this phototube can still be sold. Keeping this in mind, we now know that if we find a way to determine the lifetime of the tube, using the afterpulse data we discussed earlier, we could perform testing on a small part of the tube, which accumulates almost no damage, ship it back in just under a month, and have a good idea of the lifetime of these tubes. And the best part is, it can still be resold. We haven't lost thousands of dollars by testing it. With that having been established, the next natural step is to look into how afterpulses affect lifetime. When an ion is generated, its time of flight can be roughly modeled by this equation here. We have 2 knowns and 3 unknowns, so we need a system of 3 equations to solve for them all. These experiments are an attempt to make that system. 3 equations, 3 experiments. We start with the standard run represented here in black. Then we make variations. Now experimentation is still ongoing, but we are ready to share at least one result from these experiments. When the gap voltage was varied, it was found that the time peak here did not change. Keep in mind that each peak you see here is caused by a particular ion from a particular location. We've run a lot of simulations in SIMION, which may serve to explain this peak. Because the only variation here was the voltage within the gap that's over here, between MCPs 1 and 2. Any ions starting from this area are going to be affected, because the voltage is different here. But any ions after are not going to be affected at all. And because this peak didn't change, we are supposing that the ion that is creating it must have come from somewhere after this line right here. We're not sure which one it is yet, but we are pretty sure that it's coming from in or after the first MCP. This is by no means a conclusive analysis. But we are optimistic. Thanks to the advancements we've made, it will be very interesting to see how our future experiments play out. Thank you.